the BIS Tall Buildings Subcommittee. Ma'am has been the chairperson of the Academic Council of Kamla Raheja Vidyanidhi Institute for Architecture and Environmental Studies for over 12 years. Ma'am, we are really grateful to have you here on board for hearing your words of knowledge and wisdom regarding conventional construction practice and episcopal relief and development of tall structures from a dictionary of knowledge and experience which you have earned in your vast career. It is more than an honor for me to welcome you on behalf of our department. It is over to you, ma'am. Alpa, ma'am.
Thank you so much, Sushil. I did not give you such a long bio, so you picked it up from some other places also, which is very good.
Thank you,
But
ma'am.
the whole idea is giving a short bio is that, you want to be a little more humble. But anyway, thanks very much. And I'm going to just jump in right away. And if you will allow me, I will share my presentation. Yeah. Okay. So let me see. Can you see this?
Yes, ma'am.
Are you able to see my screen? Okay, great.
Yes, ma'am.
Yeah, wonderful. So what the topic which I've been given today to talk to you, and I'm really happy to be here with all of you, is earthquake resistant design and conventional construction of tall buildings. So, very interestingly, I thought that there are three operative phrases in this very long title. One is tall buildings, the other one is earthquake resistant design, and the third is conventional construction practice. Okay, so I'm going to tackle each one of them separately, and then we'll try and join them together, and somewhere in between also we'll try and string it together. Okay, so I'm going to start first with tall buildings. And one of the things, in fact, I would also, since, we have a lot of professors over here, I have a very fervent plea to all of us who teach structural engineering to students, that one of the things we as engineers, as civil engineers, do not do is teach history of civil engineering to our students. I think if we had a separate course of history of civil engineering, just as how architecture students have to study history of architecture, I think we would have the students more interested in understanding the whys and hows. So I'm going to start with the history of tall buildings. Okay, so when, how, why did they happen, and why were they not there earlier? So interestingly, the first tall building, when I'm saying tall building, I'm talking about a 12-story building, happened 140 years ago. Okay, so that's a really long time ago, and I'm just hearing that it is only now that in Gujarat, in Ahmedabad specifically, you're having buildings which are more than 100 meters. Which actually, if you're talking about it, is just 30 stories, right? When you talk about 12 floors, it's about 40 meters. So that happened 140 years ago, and it was built with cast iron. Okay, and if you know cast iron, it's like building with children's wooden blocks, or building a house of cards, right? So it cannot be built with any kind of rigid joints, right? And no monolithic construction. There's no welding you can do to cast iron, and all you're doing is you're working with nuts and bolts. So there's a certain limitation with the material. And then it was at the turn of the century, or I should say late 19th century, that is in 1880-90, that there was a sudden jump in the development of both materials and certain vertical transport systems and certain fire protection systems. So you had three things happening. One is you had the rolled steel sections, which happened, and then you had the elevators, the vertical transport systems, because when you have tall buildings, nobody's going to walk up 10 stories, 12 stories, 15 stories. So you had suddenly the vertical electrical elevators happening. And you had the sprinkler heads for firefighting, because at that time if you had a fire, you would need to locally be able to resist the fire or fight the fire, because you did not have those kinds of fire tender systems which could reach up to a particular height and help in fighting the fires. So then what happened is, then now if you look at it, I'm just going to quickly take you through. So then you had, at the turn of the century, at the turn of the 20th century, they also started trying to, they were building steel buildings, but then they also said, let's try this new material, concrete, which had just begun, when we are talking about 1903. I mean, it was in a very nascent stage, and they didn't even have M20 concrete. They had M12, M15 concrete. So you can imagine that a 16-story building, each column would by itself be like a fortress. So of course, they abandoned further development of concrete tall buildings up until late 20th century, right? So then from the 1950s onwards, they had started building a lot of tall buildings. We are talking about the New York Equity Building, which was built, believe it or not, more than 105 years ago. It was built in 1915. Okay, it was built in 1915 in New York. It was a 40-story building. Now, what was interesting is that these kinds of buildings, what was happening is, because they did not have this. Every room had to have natural light and ventilation, right? Now, when you're trying to build these buildings with natural light ventilation, what happens is that the only way you can do it is by having buildings with a central atrium, or you can have buildings which are C-shaped, T-shaped, and so on and so forth. And then they suddenly started having this concept that why can't we build a core which has all the elevators, the staircases, and so on. So the buildings began getting very stocky, and they were getting tall. But what was happening is that suddenly you would walk along a street, whether it's New York or Chicago or whatever, and it just felt you were walking through a tunnel, because you had these big buildings which were very tall. And so the city came in and said, no, you have to have setbacks, so that the building's footprint kind of squeezes, or gets reduced as you go higher. So you had what you call the ziggurat-shaped buildings, or buildings where the footprint reduces after the podium levels, or the first 5, 7, 10 floors. And so this was the system which continued till 1950. But remember, they did believe that you needed to have a very strong, solid base. So the base, they wanted it to be much larger. It was only from 1950s onwards, you started getting more sleek buildings. Okay, you had buildings which had a higher slenderness ratio. And then also simultaneously, what was happening is concrete as a building material saw huge amount of development. And suddenly from that M12, M15, and less than M20, in 50 years time, you had got M40, M60. And in the 90s, they went up to, M80, M90, M100, right? And so when they were going so slender, they did realize that they would have certain problems in terms of higher accelerations, both in wind and in earthquake. And wind, of course, is more frequent. So then they found different systems to handle it, such as dampers and so on. And then, of course, you've seen, I think, well, some of you are born, nowadays when I get CVs, I see everybody's born in 1995, 96 and all that. And I'm saying, I was already 10 years into my practice by that time. So when I say, oh, you all were there in 1990 and you know what it was, I believe you were not there. But anyway, since 1990s, the tall buildings moved from essentially steel buildings, which were in the early 20th century, to now at the turn of the 21st century, they started becoming concrete buildings. Now, another interesting thing, if you see in the slide, is all of the pictures, all of these buildings which I've shown right up to 1974, they're all buildings in New York or Chicago and so on. It's either one of those. So it's basically in the United States. And then suddenly you see Kuala Lumpur comes in, Taipei comes in, Dubai comes in, and so on. So what was interesting is, if you look at, as I said, so there are two things happening. One is there is a material change, and one is there's geographical change. And both are interlinked. So you had steel, which was the predominant material for tall buildings from 1930s up until the 1980s. 1990 suddenly saw, it's becoming less and less. And look at it as just about 5 years ago, because that's a slide I had, that you have less than 10% of the buildings which are in steel. A lot of buildings are concrete, and many buildings, majority of buildings now are composite structures, right? They are using both concrete and steel. Predominantly, they are concrete structures, and steel is used very strategically. So you can have, composite members, or you can have a composite system. So there are two different ways of using composite as a material, as in composite elements or a composite structural system. So why is this sudden change in terms of concrete to steel, from steel to concrete or composites? Why did that happen? That is also linked to the geographical movement from the west towards the east. In the west, labor is very expensive, while in the eastern country, or as you move towards the Middle East or Southeast Asia or Asia, material is more expensive, or it used to be more expensive as compared to labor. So therefore, that pretty much was driving the choice of material which was being used for these. Now, if you look at geographically, you can see again the same thing as I said, that, up until 1990, North America, which primarily is the United States of America, a little bit of Canada, 80% of the tall buildings, the 100 tallest buildings, 80% of them were in North America. And, today it's just about 10% or 12% of those buildings which are there. Asia has been a big driver, of course. No brownie points for guessing that, China has driven the tall building movement, and also a little bit the Middle East. Yeah, Dubai has been a very large factor. All the others are very small players. Whether you're talking Europe, I'm sure a lot of you are aware that Europe has an allergy towards tall buildings. One of the reasons is because they are very, very sensitive about their culture. So even as far as Paris is concerned, you cannot have any building which is greater than 40 meters in the core. No new buildings are allowed in the core of Paris, right? And then in the suburbs of Paris, you have to get a special permission for anything above 70 meters, okay? No, up to 70 meters, excuse me. Up to 70 meters you can build in the outskirts of Paris, and that also you have to get a special permission. Interestingly, just about a month ago, somebody went to court and they've got permission to do one tall building, and all the Parisians are up in arms. Oh, our culture, and we like our building small. So Europe has a very unique history, and they're not very fond of tall buildings. So why I'm saying all this is because everything is linked. It's as Buddha says, this is because that is. So why I'm saying this is because, you will in the course of, your teaching or your careers, you will have an opportunity to see the American code, the Chinese code, maybe the Euro codes, the New Zealand, Australian codes, and you have to understand the amount of investment they're doing in tall buildings to also understand the investment of research they do in kind of having different clauses in their codes for both tall buildings and earthquake resistant design for tall buildings. So anyway, so this is just a fun fact, that there's only one US building in the top 10, and in the future there's only going to be one US building in the top 20. But as I'm saying, these are fun trivia. So now the other interesting thing, I think that it's also about historically and culturally seeing how the world is changing, that, earlier it was only offices that were being used for tall buildings. But as it has moved towards Asia, and I think that's especially true about Mumbai and some areas in the Delhi, the NCR region, but maybe, 10 years later, it's also possibly going to be true about Ahmedabad. I don't know, but Ahmedabad has a lot of open space, so they need not go for so many tall buildings, but you know, as the movement of tall buildings has gone eastwards, you're finding that there is quite a bit of residential and, more importantly, mixed use. You know, so there would be residential come certain amount of commercial, you know, which would be there. There'd be shopping down and residential above, or service apartments above, and that's very much true about Singapore. There'll be malls below, and you have residential above, or hotels, and so on. So it's a very interesting historical kind of underpinning that one can get if you just see what is happening. And I'm just going to take you through some 3 slides, which you will see why I'm taking you through, and why, you know, this tall buildings is something which has personally hit me home. So this is New York. You can see the topmost is 1876 of New York. You know, you can see how flat it looks. And then chutput, you know, in 1932, there are these few tall buildings. And then you're seeing in, you know, this is in 1988. And you can see still those twin towers are there, which, you know, of course, in 2001, what happened, and the 9/11. And then suddenly they were not there. And now look at what the skyline of New York is in 2010. And look at, just see how much space I required, you know, for that as compared to the other slides. Look at what has happened to Dubai. Okay, this is a picture of Dubai in 1950, and you can see the Burj Khalifa over there. So this is Dubai. You know, it was really a desert, a wasteland, and in 70 years, this is what has happened. But what is going to really interest you is the next slide I'm going to show. Both the pictures, I live in a tall building, okay? I live in a building which is about 35 stories. And I have a view which is, you know, I'm seeing the city grow in front I have taken these pictures from my balcony, okay? So I first moved in 2008, okay? And this, as you can look above, I had such a big sky. I could look out and I could see the sky. And this is in November 2020. Okay, where I have, I could take it now also. I mean, I'm just showing this picture because as other pictures I've taken were of night pictures. So I just thought I'll show you this. And look at it. I just sometimes feel, my God, they've eaten up my sky. You can just see this is Mumbai. Okay, this is Mumbai. You can see how much it has grown. And, you know, in the last 2 years, of course, last 2 years were the COVID years, but still there's been construction which has been going on. And you can see I've lost half of my sky, right? But then you know, I'm sure these people who are living in this little building, which is across of me, anyway, that's a historical point. I don't think I have time to talk to you about. I'm sure they're looking at my building and saying, they took away our sky, right? So this is what we have done, and this is where the cities are going. And I mean, you know, it's not my place to say whether it's a good thing or a bad thing, but this is what it is, right? Now I'm just going to talk to you about tall buildings. Now, generally, there is a belief, and it is not ill-placed. It may not be completely right, okay? But generally, there's a belief that tall buildings don't have too much of a problem during earthquakes. You know, you don't hear of too many building collapses in an earthquake of tall buildings. See, when I'm talking about tall buildings, first of all, I'm going to use a definition we have used because tall means different things to different people. I'm going to use the definition we have used in the new the tall building code, you know, which is IS 16700, where we have said any building which is over 50 meters is defined as a tall building as per that particular code. So I'm just showing you tall buildings defined by that code, and I'm just showing you that, look, there have been, and you know, sometimes it's easy to see this, and you can see that, you know, there's a huge potential for soft story collapse. And of course, there was a lot of discussion about this building having been constructed very poorly, and when they had you know, when it fell, they found all kinds of paper and lanterns and all kinds of things in these in the construction. And of course, the developer, you know, had went to jail and so on. But I'm not sure you can just ascribe the failure to poor shoddy construction. You know, I think all of us who are an earthquake resistant design and construction can see a lot of pain points over here, right, which would have a potential for such a thing happening. And then you can also see what can happen, so these are classic failures, and I think there are lots of other people also who are going to be talking, so I'm not going to get into the failure of structures, but I just wanted to flag to you that it is not as if tall buildings have not given way. I do agree they're few and far between, and what we're talking about is this is both in the 8.8 Chile earthquake, and this is the O'Higgins Tower. But interestingly, this O'Higgins Tower was not demolished. Okay, it was retrofitted and is being reused, and of course the Alto Rio building had to go. So you can see that sometimes you have elemental and partial failure, and sometimes it's a complete toppling. So the kind of so I'm first going to respond to why we say, or why people have this impression that earthquake effects in taller buildings are generally less than in small buildings. Okay, that's the impression among engineers. Okay, but if you ask a layperson, they're always worried about a tall building in an earthquake, when actually it's 2001 earthquake was a very good example in Ahmedabad, that yes, you had some tall buildings, very recently constructed tall buildings collapsing, lots of people dying, but the number of those buildings was very small as compared to the number of small buildings which gave way, right? So what happens is that, typically the taller buildings have a much higher period, or they have a lower natural resonant frequency, okay, than the shorter ones. And typically, if you remember, what we would say is that, just as a thumb rule, that the time period of a building is 0.1 n, right? I mean, that was what used to be our standard, just to get a first feel for it. Okay, kitne माले का मकान है? Oh, 12 माले का मकान है. So 1.2 seconds will be its natural period. And what happens is that when you have an earthquake, okay, you have possibly a very broad spectrum of seismic waves, which which are released, having different frequencies, right? So we also know that the behavior of a structure is going to be dependent on the natural frequency of the building and the frequency of the waves, right? And the resonance, right? So that's the resonant frequencies. So what happens is that, when you are near the epicenter of a quake, okay, what happens is that at the epicenter, you have a large number of very sharp seismic waves of high frequency. Okay, high frequency means low time period, right? And all these small two-story buildings, okay, which have a very high resonant frequency or a very low time period, they get affected, okay, because there is a resonant frequency. Now what happens is, so the tall buildings which are closer to the epicenter, they are going to be subject to these very low natural period waves, and there is not that much of resonance. They may not be as affected as the low-rise buildings. But what is very interesting is that as the waves travel, the high frequency waves, they die off. Okay, and the low frequency seismic waves are the waves which are going to travel farther. So interestingly, so these low frequency waves are the ones with a high natural period, a high time period, right? So they are the ones which will affect a tall building which may be actually quite far away. They may be at a huge distance away from the quake, but they will be affected because of the resonance. So this is something which is very interesting to remember as to what happens. But by the time these seismic waves of low frequency go to the tall building, there's a lot of damping which has already happened and so on. So therefore, the overall effect is a little bit lesser, right? So you see, this is what you will also see, what I have said is actually captured even in the natural period versus the SA over G. right? We have in your IS 1893 part 1. So as you see, if you just look at my that formula which I said, I mean your thumb rule, okay, point 1, and nowadays no code, none of our codes given, but still you'll find in textbooks they'll tell you that for your first approximation take 0.1n. So what happens is, so if I have 20-story building, I'm here at 2. If I have 30-story building, I'm here. So you can see what is your value of your SA over G, right? So this is what is something which you can just think about and understand why so tall buildings. But I mean, just to flag one thing, that it's not as simple as I'm saying. Nothing is ever very simple, and sometimes when you try to simplify it, you kind of miss out some of the nuances. So let me just flag that obviously earthquake effects will be depending both on the magnitude and intensity of shaking, of course, and also on the duration. So that can and also, as I said in the last point in this slide, is that there is one more there's a joker in the pack, and that can complicate matters, and that is soil structure interaction and soft soils. So when we are on the Deccan Plateau, I always make a big hue and cry when I see what kind of numbers are being thrown up by seismologists, and I'm saying, Mumbai is on the Deccan Plateau. Please, I don't know where you'll get these numbers from. I mean, there has to be a huge difference between what you get, let's say, in NCR, or what you get in Mumbai, or what you get in Ahmedabad, right? And sometimes that is a nuance which gets missed out. Okay, so as I said, there are lots of parameters which will define the earthquake effects on tall buildings. But what are primarily, okay, so what separates tall buildings from not tall buildings? I think especially as Gujarat gets into tall buildings, it's like, see, what I had seen in 2001, which of course is a far cry from 2022, right? 21 years, one whole young generation has come in, some of the young boys and girls who are going to be graduating from LD College and all the other colleges. They must barely be 21 years old. So they are children, post the 2001 earthquake. So they have no memory or no idea of what happened during that time. But those of us who either were there on that day or who went there immediately after, I mean, that's something which is indelible in our memory. So what is different between a tall building? Is it just because, so the point I was trying to make is that one of the things I found in some of the buildings which at that time were called tall buildings, whether it was Mansi or, I think they were all 10, 12 story maybe buildings, and was that somehow there was an idea that it's just a vertical stretch, just as how architects do a vertical stretch in their Revit and AutoCAD and whatever, that a tall building, even for structural engineers, is just a vertical stretch of a 3-story building. That was 21 years ago. That was my assessment of the building behavior at that time. Of course, things are very, very different now, and there's a lot of advancement. I mean, Gujarat is doing, a lot of leading edge stuff. So sometimes, we learn lessons which we wish we didn't have to. But I think that one of the things which is now very clearly understood is that the main driver in tall buildings is serviceability. Okay, it is control of your deformations. It is about occupancy comfort. Okay, that is the driver. See, what is underlying in it is that obviously you are taking care of stability and safety, as you have to do for every building, every structure, right? But you also, the other thing is, there are certain kinds of behaviors which are possible in tall buildings, which may not happen in, not so tall buildings, which would be the rocking effects and the toppling effects, right? So those are the things which are special issues to be looked at in tall buildings, and that is why tall building design is very different from not so very tall, and therefore the structural system, having a proper structural system is very, very important, and especially a lateral load resisting system. Both, when you're talking about lateral loads, it's both, it's earthquake and it's wind. Now I'm going to go to this issue, as I said, that, every building has its own natural period or its own natural frequency. So what is again the difference between tall and not so tall buildings? So you see, in not so tall buildings, there, first of all, it's very often that the shorter buildings, you experience more of a deformation, which I would say is a shear deformation. Primarily it is a shear deformation. In taller buildings, what happens is it is more of a flexural deformation and a combination of shear and flexural deformation. But there is a difference in the way a tall building and a shorter building will behave in terms of deforming in lateral loads. Now, why I'm saying all of this is because we need to understand that some of the codes across the world will separate how you calculate the fundamental approximate, okay, how you will calculate the approximate natural period in a building. So they will say that for buildings which are less than 40 meters or so, there is a separate formula. And for buildings which are greater than 40 meters, there's a separate formula. So in buildings which are less than 40 meters, sometimes they may have some correlation with the planned dimensions of the building. Sometimes. Okay, some of them have done away with it, but there are some codes which still today also will say, okay, if it is a less than 40-meter tall building, it will your deformation will be based on what is the dimension of your building. So if I have to, but I'm right now not going to show the formulae for natural or the expressions for natural period in tall buildings in other codes. What I'm going to do is, because I'm talking only about tall buildings, I'm only going to talk about buildings of 40 meters and higher. And I'm going to say 50 meters here because in our code, we have called tall buildings as buildings over 50 meters. So let me take you through some of these codes. Okay, I have picked up 6 international codes. So the American code, the ASC 716, has a formula which is, I've just given you the coefficients in the metric system. And so if you see the time period is, some coefficient into the height of the building, HN is the height of the building, raised to another coefficient. Okay, and these coefficients are more or less fixed for certain parameters. The Euro code and the New Zealand code, they say just take whatever is the period you get in your, as per your analysis. And this is for your approximate fundamental period. Okay, I'm talking about that. I'm talking about to calculate your first estimate of what is the base shear. You need to have what is the approximate natural period of fundamental natural period. So both the Eurocode and the New Zealand code, they say either you take it from your modal analysis or you can use the Rayleigh method. Okay, this is the Rayleigh method, and I think any of you know what is Rayleigh. I mean, most of you would know what is Rayleigh method. Otherwise, just you can just find it out on the net. So these are the two options. The Australian code also, you'll see this, it has 1.25 times one coefficient into the height raised to whatever, another fixed number. The Canadian code also has some coefficient into height raised to some other coefficient. The Japanese code also has directly related to the height. I'm not showing you over here. I did actually a study of some 20-30 buildings. With all these 6 codes plus the Indian code plus whatever one gets from a computer analysis. And it was very interesting what one gets in the results. But now I'm going to take you to the Indian code. Now, unfortunately or whatever, the Indian code has no separation between tall and not so tall buildings, right? So we have a separation for buildings which are bare frame buildings and buildings which are structural wall buildings. Okay, now the bare frame buildings have whatever, it is only dependent on the height. But any building which has, and practically there is no building which has no, which is just bare frame building, right? Because any building you do which is a tall building, it will have at least your lift walls, right? So any building which has RC structural walls, so pretty much for tall buildings, you cannot use A. You just cannot use A. You have to use B or you have to use C. Now, both B and C formulae have the dimension, have not only the height, but it also has a plan dimension, which is there. In formula B, it is not about just the height, but it is about the area of the walls in each of the directions, right? So the other interesting thing is that there are two fundamental periods which our code talks about. International codes have only one fundamental natural period. Okay, so I'm just flagging it. So these are things which, you know, we may perhaps address in the next revision of 16700, because, you know, 1893, which actually stipulates all of this, is a mother code, and you know, it has to cater to everything. So there are limitations into how much it can, detail out and flesh out some of these things. So maybe it needs to go to some other code. But I just thought I'll flag this because this was a good occasion for me to just discuss this comparison between various international codes and how we in India look at this issue of design of tall buildings. As we all know, one second. Okay. So we first had this code, the first tall building code in India came out in 2016, right? And it is for buildings over 50 meters. I think what is also interesting in our Indian codes and international codes is that, earlier on in some of our codes also we used to have this, that this is all given in the codes. But however, if an engineer does something based on her engineering wisdom or his engineering wisdom, which is different from the code, that doesn't make the building non-compliant. See, this is a very important thing because, you know, now we are in an age of litigation. We are in, an age where people are looking at the spirit instead of looking at the spirit of what is written, they are looking at the letter of what is written. So if you look at any of the American codes, you look at ACI 318, you can look at any of the AC codes, they'll always have one statement saying that even if the engineer does something different from this code, that doesn't mean that that is in violation or it is non-compliant. But we don't have such a statement, you know. So you may have in a peer review, you know, that somebody has done something which actually makes more sense than what our code says, but they'll say, your building is code non-compliant. So I think that nuances need to be brought in. So this is the first code which has said that, look, this is a prescriptive approach. We are saying that we are giving you these, we are stipulating these requirements. Why are we stipulating these requirements? Because then we are stipulating what is a regular building, and we understand what is the behavior of such regular buildings. So if you design it based on on regularity, then we know in an earthquake mota kya hoga, and we can tell you, okay, this is how you need to design to be protecting your building. Okay, but doesn't mean that if you don't follow these particular requirements, that your building is unsafe. It just means that you need to do more rigorous analysis and design to assure yourself and the client and the user that this building is safe in all load conditions, right? So instead of calling something which doesn't follow the requirements of the code as non-compliant or in violation of the code, it is better to call them, and what we've done is we've called these buildings which don't follow this as code exceeding buildings. Okay, this is something which is used also elsewhere in the world. So we have said, okay, if your building is code exceeding, that means you're not following the prescriptive approach of this code, then you need to have a proper review committee which will then prescribe that what are the things you need to do, which is more rigorous analysis than what is the very simple approach which is given in this new tall building code. Now this code is only for concrete structures, okay, and it is only for buildings up to 250 meters, and it can be used for buildings less than 50 meters. But as I'm saying that if we give a specific a different formula for time period, a different expression for time period in the tall buildings now, but that will only be valid for buildings above 40 meters or 50 meters. That can't be valid for buildings which are 10 meters, 12 meters, because they have a very different behavior, than tall buildings. So there will be some nuances we'll have to bring in. But presently, whatever are the requirements, they would be very much valid for all kinds of buildings. So what is it that this building talks about? It tells you that, which structural system can be used for what maximum heights, and what are the aspect ratios, length, breadth, versus height. What are the drift? See, now the drift requirements are given in other codes. Okay, it is also given in your earthquake codes. It's given in your IS 875 codes, and so on and so forth. But this is a tall building code. We understand that there can be a little more relaxation in those than what is given in the other codes. So there are some special requirements over and above what is given in the other codes. So therefore, this code has also said that if there is something here which is not aligned with the other existing codes, then for tall buildings, this code's requirements will be relevant or will be valid, right? So and also it also tells you about what is the story stiffness and strength, about what are irregularities. Some of it is the same as what is given in 1893, but there are some relaxations. So more than I think there are more relaxations in this code than what are there in the others. It is a bit more strict in certain things. I'll come to that. I'll tell you where it specifies things which are not specified in the other codes, and therefore it becomes a little bit more rigorous or more rigid. So this is the laundry list, and this is the scope that you have. What are the seismic and wind effects, and cracked and uncracked properties of concrete members for analysis. So I think that there are cracked properties which are now given for earthquake. Of concrete cracked properties for different concrete members for earthquake analysis, but it has not been given for so that is for ultimate design, right? But for serviceability, that is for wind loads, I don't think the uncracked property the cracked properties are given in any other code. So that is given right now over here. And see, what we found even while preparing this code was that we don't have data in our country. Either people have data, but they are too, kind of shy of sharing it, or there's really no data. So today, if we want to know that, 30 tall buildings, Mumbai has had tall buildings since 1985. Okay, I'm talking about the first tall building, which the tallest building of 40 stories was something which I had done in 1992. Okay. So you can just imagine that, so this history of, so that's about 30 years ago, right? Now, despite that, in my own buildings also, I'm not able to get today, what is the actual natural period of that building, because there is no health monitoring we don't put in accelerometers, we don't put in anything. So I think it's time that as a country we build our own independent database, because we build different structures. We cannot compare the database which America has with us, because they have different kinds of buildings. Most of their buildings were in steel. Now they're building some in concrete, but they use very, very slender sections as compared to us. So the kind of data they'll have will be very different from our data. So it's an important thing, and this code has made it very. It's not mandatory, but it is required. Preferably that people put in all these health monitoring systems in place, and guidelines for approval process for code exceeding buildings. So I'm not going to go into details about this, because I'm just seeing that I've already taken 1 hour or something of this, and I have only actually 1.5 hours. But I'm just going to just quickly go through certain slides and just say, what are the things that have been moment frames can't really be used beyond 60 meters. That also just in moderate seismic zones. And in higher seismic zones, just a moment frame for a tall building doesn't make sense. Anyway, anyway, you can't have a building without elevators, right? Which is a tall building of 50 meters or higher. So you anyway have a have a shear wall. So you need to come. The second thing which now has been changed is that when you're doing a structural wall system, don't have everything just in the core. Okay, you need to have some walls also distributed elsewhere. Otherwise, you have a combination of a structural wall system and a moment frame. So have a moment frame along the periphery, and the core can be structural walls. Or you can have a frame tube. And there are restrictions which have been specified in terms of height for each of the structural systems that you can use. Same thing, there are slenderness ratios. What you're seeing, all these crosses and all, are just, I'm telling you, I'm just kind of pointing out that there have been some changes in the code, in the amendment, from what was the original 2016 code. So there are these slenderness ratios also which have been specified. Another point which I think has been giving a lot of grief to everybody says, and this is something we will have to review, because that what we have said is that the torsional mode pretty much has to be the third mode. It cannot even be the second mode. Of course, it can't be the first mode, but the torsional mode has to be less than 90% of the translational mode in the X and the Y direction. And irrespective of anything, you can't have the natural period greater than 8 seconds. Okay, because it just means that the building is very, very flexible, and you will have problems in terms of occupancy comfort, right? So, and then, there are all kinds of specifications on, you have your floor diaphragms, and where can you have cutouts, because your floor diaphragms are really the load path for your lateral loads. As I said, that drift control and lateral loads drive the design of tall buildings. And so you need to have a very clean, well-defined path for your lateral loads. The diaphragm is the path, and so giving sudden cutouts will confuse the whole load path system. And so you need to be careful about that. Also that, there's this whole concept of buildings need to fail gracefully, right? So therefore you cannot have sudden collapses, or you have to identify that you have a second line of defense. If the first line is going to give way, the second line of defense has to be something which is going to be able to make the building stand, so that life safety in the most the maximum credible earthquake you can possibly have, you at least want to ensure life safety, right? So you want to have an alternate load path, and you want to make sure that the building is able to sustain its integrity for the time that is required for safe egress of the occupants of a building. And also, sometimes you have key elements. I mean, even if it's a gravity load system, you can have a lot of columns coming onto some transfer girders, even if it's gravity, but you need to have, those are key elements, right? So they cannot fail. So you need to have certain guidelines about how and which way they should behave. And what we have done, again, this is a relaxation. There's a minimum base shear requirement that you have in 1893. And for buildings which are, over 50 meters and, greater than 200 meters, this gives you a lesser base shear coefficient than what you get in 1893. Okay. So then, and also, as I told you, that there are crack section properties which have been given for both, ultimate and for serviceability, that is for wind and for earthquake. So you can see that whatever is given on the right hand side, which is for earthquake, 0.25, 0.35, 0.7, 0.7 for slabs, beams, columns, and walls respectively. In the serviceability, it will be obviously relaxed, because you are not going to the ultimate, you're not cracking your building as much, right? So therefore you will be able to see that there is, but you can't design it for full, the full IGROS, which is what people do right now in the app we're doing right now until the this code came in. Then there's a lot of discussions on the backstay effect. Okay, the backstay effect is that, you have a tall building, and then you have a, and it's a slender tall building, and then you have a very large stocky podium of 2 stories or whatever. So what happens is that, just think of it as a pendulum. You have a pendulum, inverted pendulum, and it is at a fixed base, right? The leftmost, as you see, and then it's very clear that this shear over here is going to be the same as your lateral force, and your moment is going to be the force times the height. Now what happens is that, suppose if I give a support here, at this grade level, so that I will call it as a place where you have the podium. So suddenly now, from this tall, slender tower you come to the podium level, and now what happens is that the lateral load can now just travel across. I mean, it has a support, right? It's that this building is now not going down completely. But suppose theoretically I've given a fixed support over there, then you can, just from first principles, you will find out that your what happens interestingly is, at the bottom you will have your shear force in the reverse direction. Okay, and your moment also will be in the reverse direction, because there is a huge amount of fixity at this point. In reality, this is not you don't have pure fixity over here, right? So it's more like a spring support you give, and that is the behavior that you get in a building with a large podium, and number of podiums are what they are. So this is a very important thing to understand. And what is happening over here, that because you have this podium level here, so it's a kind of a support, but not a rigid support. So there is going to be now a transfer. The diaphragm is now extended, and the load path suddenly changes of the lateral loads, right? So therefore, this diaphragm is very important to be designed properly. And then suddenly, if you have cutouts and so on in the podium level, which very often you do have, there are issues. So there is a huge big chapter in this code about what to do about buildings with podiums, and taking into consideration this backstay effect, because this is what you get, right? This backstay over here. I'm not going to get into all of this because it's a very detailed chapter. Do go through it when you have the time, especially, I mean, since you all are now doing a lot of tall buildings, and I'm sure there is podium here, but you can, you have all these different irregularities you have in IS 1893, and some of these kinds, whether it's torsional irregularity, certain kinds have been specified. The seismic forces have to be amplified by a factor of 1.5 for designing of the connections of the diaphragms to the vertical elements and to the collectors and so on. And for irregularity of the diaphragm cutouts, okay, which is a very major thing, the seismic forces have to be amplified by an overstrain factor of 2.5 in the design of collector elements and connections to vertical elements. So these are nuances. Have a look at all of these clauses. If there's any issue, you can always talk to us through the code committee or whatever. You have some ideas, maybe you think that there's something you have a good suggestion. We are always open to that. And there's a minimum requirement of what reinforcement you need to give in the first topmost podium. Okay. Now in structural walls, when you're designing it, again, there's a lot of relaxation that, if you have a less than 800 millimeters or 1/3 the length of the wall, whichever is lesser, there is an option to ignore those walls, because you still have a very good load path. And I'm not getting, then this very interesting thing which has been discussed about when you have gravity loads, what is the amount of the wall, because very often I find that you have beams which are 200 wide, and they're carrying a lot of load, and then they come onto a shear wall in the weaker direction. So actually they are only on that wall of 200 mm wide by whatever, by 200, let's say the wall thickness is 200. So sometimes there is a huge amount of bearing stress also over there. And so but people just assume pure mein ja raha hai, puri itni lambi wall hai, are baba, but it is only the gravity load is only going to that point at that particular location in that floor, and it can only spread so much. So what is the spread that you're allowed to consider? And remember that your edges of walls or the boundary elements are the most impacted in an earthquake. So there are all of these. Okay, then the other thing which I would like to point out is that, when you have axial stress, which is compression, it helps you in shear. But when you have your walls, sometimes in tall buildings, the other difference is you can actually have some walls go into tension, right? Which doesn't happen in small buildings. So when you have tension and shear, it's bad. Okay. So then what happens is you have to understand that the design shear stress of tau c is not there in your concrete. Okay, there is that shear stress is not there because your tau c has been assumed that your element is in compression, but now you have your element in tension. So in that case, this code very clearly says that your nominal shear stress can only be considered to be 0.5 tau c. Okay, that's another important thing. So I'm not going through the whole code. I'm going to now just quickly. Yeah. So these are not things which are very important. So I'm not going to. Okay. Then what is the minimum requirement? Now a lot of times I find people considering these as similar walls. They use IS 456 to design it and say, अरे उसमें तो point walls का तो minimum requirement तो दिया नहीं है इसमें. तो वहाँ तो you require only so much 0.2%, this, that, and the other. But so this one says, no matter what, you will give 0.4% steel in the vertical direction. We have changed the requirement in the horizontal direction. That's an amendment which has come, or which will come, whatever. I think it has already come. But so the vertical, the minimum steel you will give is 0.4%. Horizontal, you'll give based on what is requirement. Foundations, again, you want to have a very clear load path. And the factor of safety against overturning and sliding will be a 1.5 for unfactored design wind and gravity loads, and 2.5 times the design earthquake load and unfactored gravity loads. I think, again, that's a very important thing to understand. Why have we said that? Because in the design earthquake load, remember, you have reduced the load by a factor of R, response reduction factor, right? So that is why this has been brought in over here as 2.5 times. So basically there, what has happened is that R has been reduced to R by 2. I mean, assuming that, your R was 5 or so. Then basically you should have at least a minimum of 3 boreholes in the tower, and you should have. So then what was happening is that we had said that when you're doing your boreholes, you should have at least a depth of 1.5 times the estimated width of the foundation. So sometimes you have a podium which is so huge. So we got feedback, "Arey yaar, ye to kya ho raha hai?" So that's when we said, okay, let's review it. So now it's not the width of the foundation, but it's the width of the tower footprint. Okay. And you do need, see, as I showed right in the beginning, you do have toppling of these very rarely. Very rarely you've seen a toppling of but in an 8.8 earthquake, anything which is 8 plus magnitude earthquake. There is a possibility of these things, and as I said, these are affected by the short frequency component of the seismic event, seismic waves, right? So what happens is that you want to make sure that you're quite safe under for toppling or for rocking, for that matter. So there is a certain embedment length for the rafts and the pile foundations which has been given. And of course, the point has been said that, if you have rock, if you have hard rock, we can't do all of this. You don't need to do it. So that also has been specified. And, the soil structure interaction for 150 meters should be considered. But otherwise, for smaller buildings, that there's a relaxation. The other thing is the settlement of foundations. Earlier, I think there used to be this thing, everybody thought it was 75 mm. But actually, even if you read the soil code properly, it's not purely 75 mm. So anyway, we have clarified it and said it can be 125 mm subject to maximum angular distortion of 1 by 500, right? For non-structural elements, there is a whole laundry list which has been given, and you can just to understand why and what and how, the background information you can see in this download, which was a very good a book which has been written by Professor Murthy and team. The structural monitoring, as I said, we do need to have all this information, this data, which we don't have in our country. So we've said, okay, you need to have these kinds of accelerometers, and for wind, you need to have anemometers and the accelerometers, and also for foundations. See, we need to have data, because then, as a country, we can save our resources. When you don't have enough data, you're always going to be working on the side of over caution, over safety. The more data you have, more confidence you have, and we can reduce the resources we are using in the design of our buildings, and so it's going to be a national saving. So that is why I think if we are patriots, we should actually do a lot of structural monitoring for our structures, so that we'll be saving national resources. So what is a code exceeding building? I'm just going to give you this. This building is a Zaha Hadid building, and see it. I mean, I'm not going to say anything else. Now, I really would not know, looking at the building, how it's going to behave. Okay, so this is a code exceeding building, and it needs to have a lot of rigorous peer review and another state empaneled committee to actually be confident about its behavior in an earthquake. After all that, also, I don't know. So these are the kinds of interesting buildings which need to go through a rigorous peer review and an ERP, engineering review panel. Both things, they are separate, but both need to be done. Okay, and there are these guidelines which have been given in this code, and anybody can have a look at it. Now, because the last point was about conventional formwork in tall buildings. So see, now I was not asked traditional. Okay, I was told, tell us what is a conventional. Now, conventional means what is a convention? Okay, so in today's time, the convention and therefore conventional technology which is being used for tall buildings, and I'm talking about really tall buildings. I'm talking about 25 stories plus, and large projects. So if you have a project which is 1 million square feet and you have to finish it, in today's time, the only way you make money is it's volume based. It's a volume based game. It's not like in one project you can make your bungalow or whatever. So it's about one project of 50,000 square feet. You can't. So it's about making hundreds of thousands of square feet in a time bound way. And so your profit per square foot is not very large, but you're doing a lot of square feet, right? So how do you build a lot of square feet in a very short time and at a very good quality of construction with great accuracy? So there are now systems available. So one of the most popular, and I would say 85 to 90% of large projects, and I'm saying, when I say large, I'm talking about 500,000 square feet plus, would be using modular formwork. There are lots of companies which both Indian and imported modular systems which are available. They are very fast to assemble. They are lightweight. And there is a lot of assured accuracy, and because everything is planned beforehand, the planning of the form work is done 4 months before you are going to actually break ground, because it takes 3 months for them to prepare all of it. So the other good thing is that afterwards, architects do they have to also be disciplined. They can't make changes, because once the form work is done, no changes. So that's good for us as structural engineers. So there are less complications. It's lightweight. And everything is very standardized. It's like it's in a way, it's like a child's Lego or some such thing, that everything is in fixed sizes and you just have to assemble. Or not Lego, I would say IKEA. It's like IKEA furniture. You can just order it and everything is so standardized, so accurate, so perfect. You can actually yourself, just assemble everything. So that's how these kinds of components are. No cutting material at site, very fast. You require very comparatively much less labor at site, very less. But this, I have a different view, because the problem in our country today is unemployment. So trying to bring in driverless cars or these kinds of technologies which use less labor, I don't know for our country if it's the right way we are going, but for the developer, obviously it's a much better way of going. And also, actually, this is something which actually you can interchange with. If suddenly one day you want to build one more building, you don't have enough, you can use even conventional. No, nothing lost. One of the problems everybody asks me again and again is that when you're doing this modular formwork kind of construction, what happens is everything is concrete. Okay, your partition walls are concrete, your external walls are concrete, and of course, external walls they will it will become a soft story if you think about it, because you're going to have parking and all that. So everybody's like, but there are ways of non-structural concrete walls, how you can make them as infill walls. You're going to cast it along with the rest of the walls, okay? But what you should do is through your detailing. So I personally, this is my way of detailing it, and I don't have any problem in sharing whatever I do. There's no state secret, and all of us are going to die one day. So there's no point in not sharing what we know. So what generally I do is, I anchor these partition walls, which are also in concrete, which are going to be cast along with everything else. I anchor them to the top, to the slab or whatever is there over there. Sometimes you have a beam also for modular construction. So I anchor it to that beam or slab or whatever. But here it's for all practical purposes, I just give like a 10-20 kind of anchorage into the lower element. Okay, so and likewise over here on these sides also I just give the most minimum 50 or some such thing. So basically it's just, these are actually walls which are for practical purposes hanging, but of course they are anchored for 10-15 So in a case of a very large earthquake or something, obviously this is going to disengage. Sometimes if a client, see, all clients don't agree to this, but our drawings will always show that you have to keep a tar paper here, or you have to keep a Shalatex board over here, all these four sides, we keep a separation material. Okay, you can keep anything. Now you can, this is what they also give in Japan, which is very similar to what, but they've shown a much larger kind of a gap over here, that you give a slit there. Now, how do you fill the slit, right? So those are kinds of questions. So this is what I find as a good way of doing it, that, you just kind of give a kind of some board over here on the two sides, so that when they're, and that is already put before the concreting. So it will allow you to have the separation, and yet, you see 24/7 you're only having gravity load. You don't want these walls to give way in gravity. You don't want them to give way even in an earthquake, but you don't want them to participate as a stiff element, or an unintended stiff element, right? So that is where you have to be, I think, very careful about how you detail your structures. And the other one is, of course, tunnel form. See, tunnel form is a problem that, everything goes in one way, this goes, and I'll tell you what the problems are. So it has, if it's done well, it has good earthquake resistance. So I'm just showing you this project in Turkey. Okay, so this is a very good project because you have vertical walls, you have, walls in the X direction, walls in the Y direction, perfect, but still, you see, actually you have nothing along the perimeter. But still, I would say it's very good in terms of very good distribution of lateral stiffness. But now you look at this. I know the color is not very good, but I mean, I just did a cut paste. See, look at this. Okay, just look at this. You can see that there are walls in this direction. And actually, if you see properly, I'm sorry, maybe you can't see this, but there's actually hardly any walls in this direction. And that also, they are right in the center. So I don't know how they avoid torsion as the first mode. Okay, but there are lots of such buildings. These are actual pictures from some particular project. I don't want to name projects, but I don't know how they can manage not to get torsion in the first mode. But maybe they do something which I don't know about, and there's a smart way that they're doing it. So I'm just pointing out that tunnel form is great, and especially when you're doing slum redevelopment, or you're doing some redevelopment projects. Not even slum; it could be just rental property redevelopment. This is a good way to go, but as I said, if you do it this way, that's great, but then you do it this way, I don't know, I'm not sure I understand how the structure behaves. So there are lots of such nuances. I think I'm going to end over here, and I'm going to stop presenting. Thank you very much for being patient. Yeah.
Wonderful session, ma'am. Thank you very much for this session. We are really grateful. From history of tall buildings to the very detailed necessities to implement while designing, importance of putting health monitoring systems which can gather more data, that also you have emphasized. We are really grateful for this session, ma'am. The session was so insightful that frankly I just didn't want this 1.5 hours to end. Also, I would like to extend my gratification on behalf of this of Applied Mechanics department. So with your permission, Alpa ma'am, I would like to open this session for questions.
Sure.
Okay, so those who have doubts, they may raise your hands, please. We will give the right to unmute you. You can unmute those who have raised the hands.
This is Lokesh. Am I audible?
Yes.
Yes. Yes.
Good morning, ma'am. I have a couple of questions. One thing is you had mentioned that we can use around 0.4% of steel in the vertical direction, and in the horizontal direction it is as per design. But could you give us some general thumb rules on what range we will get it in the horizontal direction with respect to percentage?
So let me tell you, that's a good question. See, in the lower floors of a tall building, my general experience has been, especially where up till the point that you require boundary elements. You know, there is a certain floor level up till which you will require boundary elements, right? That is based on what is going to be the stress ratio that you have in that, and those boundary elements are going to have to be designed for the same lateral reinforcement, the same shear reinforcement as for columns, right? So now, what is see again, now this is a design issue. See, everything in design cannot be codified, right? So what happens is, if you're going to have a shear wall whose gravity axial stress ratio, okay, forget about what's happening in an earthquake, just your gravity loads are such that your axial stress ratio is already 0.35 or 0.3, anything over 0.3, frankly, your whole wall should be detailed as a column. Okay, because if you know that there is a requirement in IS 13920 that you cannot have an axial stress ratio of more than 0.4, right? So you can't use a loophole that in walls it has not been specified. Now, of course, that loophole has been also revised in the amendment which has been given to IS 13920. So now I know I'm giving a very long and rambling answer to your point, but the reason I'm bringing all this in is that, so if you design it correctly as per what is required from you for your design, you will find that for the lower, I don't know, see, I'm talking about, let's say, a 30-story building. So I have found typically, and let's say your axial stress ratios in the lower floors are around even in the walls are around in the range of 0.3 to 0.35. You will find that in the lower floors, your horizontal reinforcement is more than your vertical reinforcement. Okay, you will find that.
Okay.
Do not be surprised at that. You will find that as you go higher, and then what happens in walls is in the upper 4, 5, 6, 8 floors, you'll find that your stress ratio is less than 0.1, or actual stress ratio is less than 0.1, and so on. So in such a case, you will find that your actual requirements for horizontal steel are minimal. Okay, they are minimal. It can go as little as 0.2% or 0.25% also.
Mm-hmm.
See, that is then, of course, IS 456 also says regardless of anything, you have to give 0.2% steel, right? Yeah, so therefore, see, earlier we had 0.4% was the most minimum. Now we are saying just check if 0.2% is adequate, then give 0.2%. But this will happen only after your vertical your actual stress ratio has come down to 0.1, or now it is 0.08. After that, you need not have a high lateral shear reinforcement.
Okay, ma'am. Thank you, ma'am. So my second question is, in slide number 50, you had shown a particular plan, which according to you was a good configuration of elements in both X and Y axis. Could you just give us some of few examples or ways in which you can identify a plan as ideal with respect to earthquakes? I mean, would you recommend radial as a good thing, or is it?
So,
I mean,
so
it just some simple guides.
yeah, so you know what happens if I look at a box, okay, if I look at a box along the two horizontal edges, okay, you want to have horizontal walls, okay, let me just see if I can I don't know, can I do that? Let me try. Um, so let me see if I can share some. Okay, just give me a minute. Okay, so let me share a blank. Okay, so now what I'm going to do is I'm just going to draw okay, so if this is my building, okay, now this is my building. Typically, I would say that I will have some, I'm going to say that I have some kind of a core over here, you know, your walls and your elevators and your staircases and all of that. Now, what will really be very useful for me if, that I provide, if I provide a what is most effective. Okay, I'm just going to tell you that what is most effective over here would be having this wall over here and having a wall like that over here. If you're asking me in terms of shapes, and you asked me what is most effective, will you get it? I don't know. Will you get it? Possibly not, but if you get it, you must hold on to it with dear life, because that's possibly the best thing you can get. Okay, so the best bang for your money you will get like this. And then what you should have is some stiffness over here, which is some stiffness, whether it is something here. I mean, it need not be a square thing, it can be an L-shaped wall or whatever they give you, or some such thing. But I mean, you get the picture. I mean, it's on all four sides, right?
Yes,
now, unfortunately, that's not how people will give you. I'll tell you how people will give you the walls. People will give you over here these walls. Ulta, they will always give you ulta. They'll give you this wall, they'll give you this wall here, and over here they'll give you this wall and this wall. So you get these walls in the wrong direction like this. So it's not very helpful.
Actually, why does that happen, ma'am?
Sorry?
Why does that happen, ma'am? Why do people prefer to have the wall that way? Is there any advantage in that?
So I'm just going to close this. And so this happens because we as engineers need to remember that the buildings are not being made so that we can give a correct structure to it. Buildings are being made because people want to live in it, and people have certain requirements that my bedroom has to be like this, and my bed has to be like this, and my window has to be like this, and the view I have to get is like this. So, or my office, windows have to be like this, and my conference room should have this view and that view. So, see that, it's something we also need to understand, that we are here to serve certain functional needs. And how do we engage with the client? How do we engage with the architect? How do we engage with the user so that it's a win-win situation? Unfortunately, as engineers, we are not very good communications people. So we also have this thing about my way or the highway, right? And the other thing, which I have seen, that architects treat us as if we are like just equivalent of plumbers, or we are equivalent of their carpenter or electricians. That's the amount of respect they have for structural engineers, because I think we have not been able to engage effectively. We have to be better salespeople for our structure than we are. So, we have to say, Asha, what do you want? Okay, try and understand what they want, and then give them options they've not thought of. But most of the time, they will give us a plan, and we assume that plan is the final plan, and then we'll try and put in our members, and they'll say, pagal hai, yahan pe thoda milega, and acha, yahan pe karo. And then, we are working with a very compromised structural system. I think it's more about our being unable to engage with them. Let me tell you, internationally, the kinds of things that structural engineers kind of do, of course, they're paid fees, which are like, many times more than what we have. But, let's keep that aside. but the amount of engagement between engineers and architects and with the client, sometimes you're working directly with a client, I think it's much more. And if we can explain to them, I think that our structures would be structurally more desirable, and it would also serve the needs of the project better.
Yes, thank you, ma'am. Thank you a lot. Thanks a lot.
Hello, ma'am. Hello.
Yeah, tell me.
Ma'am, my question is regarding the damping. If suppose we are providing the dampers at a certain interval floors in the tall buildings, so can we reduce the drift ratio?
Yes. So you are providing a damper, what, at 2/3 height or whatever. Typically, dampers are 5% of your building weight, and you have a at whatever at the top, or you have it at 2/3 height or whatever. So what is the question? I'm not sure I understand.
Ma'am, wind dampers.
Yes,
For
wind
this
damper.
type of.
The question is, they will help you. There's no doubt about that. They will of course help you. Now the point is that first of all, I don't know what it is right now in other parts of the country, but I do know that and especially the 16700 also requires you to do a wind tunnel analysis. And what is very important is that it also allows you that if you do your design as per 875 versus the wind tunnel analysis, and you get you get slightly lower results from the wind tunnel analysis, you can use those subject to I think it is 70% or something. I could be wrong, but 0.7 times what is there in IS 875. Right. So what happens is that you may find in our country, because the wind, it is as of now, what are the wind forces that we design for? Very often the requirement for dampers for regular buildings is limited, unless you have a really small footprint of a building. But typically people still have large enough footprints that your drifts are within the allowable limits, and more importantly, your accelerations have to be within the allowable limits. So those acceleration limits have been given in the tall building code.
And my second question is, when we are calculating the natural frequency, because a lot of codes, there is a different parameters they are taking for the considering the codes. So can we suggest, or as a researcher, can you suggesting some parameters for improvising?
So see, no, that's a good question. I think that we are looking at a possibility of introducing a separate expression for natural for calculating the approximate natural period for tall buildings, separate from what is there in 1893 for buildings over 50 meters. We are, there is a serious consideration about that, and let us see what happens. I think we will see some movement in that direction, because there has been quite a bit of studies done about what we are getting as per different codes, 6, 8, 10, 12 codes. See, what is interesting is that, forget about Indian code. Indian code gives you very low time periods as compared to rest of the, not in other buildings. Okay, in regular buildings you'll get not very different. But if you have, let's say, a very long building, okay, you have a building which is not a regular building, okay, which is not a regular building, then this Indian code approximate formula gives you very different results from the rest of the international codes. So it is those outlier buildings which need also to be addressed, and that is why maybe we can have I mean, there is a possibility of looking at an alternative formula. So right now, see, the thing is, it depends. I mean, the way people read it, that if you don't use the code specified natural period, then you are actually doing a non-compliant building, right? Because that natural period is going to define your base shear. So therefore it's a very tricky issue. So right now, if you need to yourself have a lot of depth within you to understand why the Indian code may be giving you results which are, actually they're incongruent, let's just put it that way. And then your peer review also has to feel it, because the idea, see, you should never do something because it's going to make the building more economical. That's a wrong way of doing it. You should do what is the right thing, because there are very many things which we do where we feel that the code is not conservative enough, and I will say no, ye aise hona hai. Just as as I said that when you have shear plus compression, your compression helps in the shear capacity of concrete, but you have tension and shear, then actually Tausi is very unconservative. So in such cases you have to use your good engineering judgment and say, bhale code allows me to do Tausi, I should use less than Tausi, right? Likewise, sometimes if I find that the code formula is giving me, approximate one is giving me some really incongruent result, what do I do? Can I do it as per ASC? Can I do it as per some other code? Now that is something which is between your client, it is between your municipal corporation, it is between your peer reviewer. I'm not going to be able to give any comments on that, really. As I said in the beginning, other codes allow for an engineering judgment. Other codes around the world give space for engineering judgment. I'm not sure the Indian system, allows for that. Yeah.
Thank you, ma'am.
I guess no one more has any questions. So thank you very much for this wonderful explanations, ma'am. Also, I would request you, ma'am, that kindly share this PPT presentation with us, ma'am.
Okay. Okay. Yeah.
If possible.
Thanks. Yeah. Sure. Thanks very
Yes,
much. Thanks to all of you, and special thanks to Professor Bharti. Really appreciate his also being there, and to all of you. I mean, I'm sure I know everybody, but I'm just seeing initials, so I can't recognize who is who. So greetings to all of you, and thanks very much. Yeah. Okay. Bye. Bye.
Sorry, how are you doing? All well?
The next session will start at 12 p.m. Till then, we have a break. Thank you all for attending.